By Seth Chaiken at State University of New York, Albany, on, well, you can read it, an extensor tree theorem and the Tutte identity for graphs with distinguished chord edges.
Okay, yeah, well, let me again take, like other speakers, take an opportunity to thank the organizers for organizing the conference and inviting me to come and enjoy it, as well as all the other participants and speakers who will fill in every well, anyway, there's a lot of stuff that's peripheral to this which I can't really, or anyone else can fit in. Well, my talk, I'll quickly introduce the matrix tree theorem, what we mean by a Tutte function, how a classical physics application, and then develop the machinery, which includes exterior algebra, which, as far as I could present here, is formally equivalent to some of the things that are done with the Grassmann-Berizin integral. And then I'll give the detail of the main result, and then try to cast this and show similarities that can be ferreted out from it, and close with an example. Let me just mention that if anybody's really cries out to see the example, I could skip to the example and show you that. Okay, the matrix tree theorem is that every minor of the Laplacian, or more accurately, every cofactor of the Laplacian counts the spanning trees of a graph. I think people are familiar with the Laplacian. I'm not going to give any references because there are many proofs and applications dating back to Kirchhoff and Maxwell, other than to say from reading the papers, they did not discuss this, and Kirchhoff or Maxwell did not use determinants for this. Okay, you could throw weights around, put weights on the edges. We get the so-called multivariate matrix tree theorem, and count the spanning trees by weight. Now, in general, that spanning tree counting function, well, I'm throwing in complementary weights as well. The spanning tree enumerator function satisfies the deletion contraction identity. It's very easy to see that by arguing that every spanning tree, that given an edge, any spanning tree either contains the edge or not. And if it contains the edge, then it's counted in the deletion graph where you delete that, the contraction graph, contract the edge. And if the edge is not in the spanning tree, it's counted in the graph obtained by deleting the edge, and vice versa. The combinatorial proof of this identity. Okay, now in addition to the additive identity, the tree counting thing satisfies a multiplicative identity if you separate the graph at a vertex. Now, some other Tutte functions. So a Tutte function for us will be a function that satisfies these two identities. The proper way to think of it is in terms of matroids, and when the matroid is separable, then the multiplicative law holds. These are the details I'm skipping. Okay, among famous chromatic polynomial, a subject of this conference, the Potts model, etc. It's the theory. It really belongs to that of matroids. And we're going to hear another speaker speak about multivariate Tutte polynomials and exactly what the conditions are for them. The range of a Tutte function in the literature is usually a commutative ring. But now another comment, tree counting has applications to physics. I needn't say that in this conference. But my question that motivates some of my thinking is, are there physical motivations for the theorem itself, not just the problem? Why you count trees in order to solve some physics problems, but is there some physics ideas behind the theorem that says this funny determinant counts the trees? So what we're going to do is present a Tutte function whose range is an exterior algebra. An exterior algebra is anti-commutative. It's basically the algebra that was mentioned in the last talk, that there are some variables that are anti-commutative. This Tutte function will generalize the determinant of the Laplacian. Now, so the physics application will be that our Tutte function value, when the graph is interpreted as an electrical network, represents a solution to a physics problem. So this will emerge, I hope. Now, the simplest case of the physics problem that's solved in this fashion is the problem to find or study the equivalent resistance between two nodes in a resistive electrical network. But we're going to add some extra formality for reasons that perhaps would become apparent, but for which there's some discussion is warranted, but we don't have time to go into that. And indeed, I had conversations that indicate that the further development of the purpose of this would be important. So we make P. I'm going to use P for this kind of thing. P denotes a dummy or added edge. We will call it a port, and its purpose is to mark for an elementary introduction to its purpose is that it simply marks the two endpoints. Okay, then we're going to use R, P, comma, P instead of R vertex A, vertex B to denote the equivalent resistance between the ends of the port. Now, this quantity, the equivalent resistance, is not a Tutte function, but it's equal to the ratio of two functions of the graph. The first function is the tree enumerator of the graph after the port edge has been contracted, and the denominator is the similar enumerator of the graph obtained when the port edge is deleted. So that's what these M's are. For simplicity, assume the graph is connected. If not, then formulate this in terms of Matroid theory. And I'm using the ratio notation so that the formula works even when the equivalent resistance is 0 or when the equivalent resistance is infinity. So that's Maxwell's rule. You count the trees in the graph when you identify the terminals, count the trees in the graph where you don't identify the terminals, and then the ratio is the resistance. Oh, GEs are the resistance of each edge is expressed also by a ratio, the ratio of the variables, the multivariables in the Tutte polynomial, the weights attached to the edges.
So the resistance is really RE over GE?
Yeah. So if you want to use resistances, just take the GEs to be 1, and if you want to express it in terms of conductances, take the REs to be 1. Okay. This is a okay. Anyway, let me back up. This is a trick that's due to C.A.B. Smith, who wrote a paper entitled about patroids, pairs of matroids, back in the 70s. That's an attribution to that. He called the anyway. That's what he did. And it's a cool thing to do. So now, if you observe the voltage and the current accessible at the two terminal vertices, I'd rather think the voltage and the current that pass through the added edge, and you measure it in the lab, you just measure two quantities independently, just two quantities independently of how many edges and vertices there are in the network. So, and then the fact that the equivalent resistance is RPP can be expressed, that together with Maxwell's rule for RPP being the ratio, can be expressed by a simple matrix equation. Okay? So we can say that the solution space projected on the two coordinates, voltage and current on the port, is the orthogonal complement of the row space of that matrix. Okay? So let's add some baggage and present the row space of this matrix as the one form on the covector PV and the covector pi for voltage and current with coefficients counting the trees, which can also be expressed as with dVp and dIp. So why bother with the exterior algebra in this context? Well, the two coefficients, I took a negative of one of them, each satisfy the Tutte equations separately. But so the vector of them, or the one form of them, also satisfies the Tutte identity, the additive Tutte identity. This is going to be an expression for the quantity that my things generalize.
Oh, you haven't yet.
I haven't yet defined it. This is the formula this generalization of the fact that this row vector, as a function of G, satisfies the identities.
So you will introduce.
I will, yes. So upon introducing this function m sub e, we will see that this function generalizes to any number of ports the tree counting function, which is the determinant of the reduced Laplacian. So now this quantity is going to be a p form over the quotient, the ratio field of could be the reals extended by the parameters r's and g's. It's over 2p. The vector space of dimension 2p, and the objects are p forms, half the dimension of the underlying space. They have 2p choose p coefficients.
What are the two p real variables? Those are voltage and current on the port?
Yes, that's what it's going to be. Each of the coefficients will satisfy its own matrix tree theorem. In fact, each of the coefficients will be a determinant. Okay, each coefficient and the form itself is a function of all graphs with some set of distinguished port edges, where the distinguished edges hold labels coming from a common set P. Okay, it's unique. No two edges have the same label, but we use the P's to label the edges and get P forms as a result. Now, the coefficients are components, language that it would be familiar to some people in the audience, more familiar than this would be, that the coefficients are components of an antisymmetric tensor. The rank of the tensor, the number of subscripts, is P, and the tensor lives in a 2p dimensional space. So what we're going to do is commit mathematical doing something horrible mathematically and drop the distinction between k forms and k vectors. Work over the exterior algebra generated by basis vectors S. So now let's see an application of what will turn out to be an application of the. Let's look at first the special case of the result I'll present for where the number of ports is 2. There are 2 port edges, and this will reproduce some known results and give a determinant-based proof of another result. So with a 2-port electrical network, there are 4 variables associated with with 2 pairs of terminals. They are the currents in each of the ports, and the corresponding voltage drops at each of the ports. There are 2 degrees of freedom in such a system, and so the feasible values for these variables are constrained by 2 independent constraints. So we can write a characterization of the externally observable behavior of the network by this equation on the variables I1, I2, V1, V2. The row space of this matrix can then be expressed by the exterior product of two rank 1 covectors written like this. So the wedge denotes anti-commutative exterior product, also known as, also sometimes thought of as Grassmann-Berezin multiplication of such anti-commuting variables. So when you expand this out, you get perhaps you could think of them as formal products of these anti-commuting variables where monomials are equivalent under permutation with a change of sign given by the parity of the permutation. The coefficient of each monomial is a determinant taken from this matrix. Any questions about that? Pretty clear.
The second row is mislabeled.
That's yes. It should be 2's in this. Thank you. I'll fix it before we put it up. Okay, so let's see how these minors, which are the coefficients up to a common non-zero multiple of the form, let's see how we can use the values of these minors to express things like the transfer resistance from port 1 to port 2. The transfer resistance is the voltage drop, the potential difference from the end point of port 2 to the head of point 2, the voltage at the tail minus the voltage at the head. It's the voltage appearing across port 2 in response to unit current forced through port 1. Okay. Ordinary resistance is the voltage that appears across a port in response to unit current that flows into the port, the same port. Here we have one output port and one input port and one output port. That's the transfer resistance. Okay? Well, that is the physics problem is the current through port 1 is 1. The current through port 2, where we put the voltmeter, is 0. We don't care what the voltage at V1 at port 1 is going to be, but then the voltage at P2, using my sign conventions, is minus positive R P2 P1. So R turns out to be positive usually. Or that, well, it turns out to be positive if it was measuring it positively. Anyway, so using Kramer's rule, the amounts to just Kramer's rule, this could solve for V2. It's the ratio of two minors. Now, the result I will present will be a generalization of the fact that the numerator if you could cancel out common factors and find that the numerator can be expressed as the sum over common trees in two graphs. The common trees are a tree is common in the graph where one port is contracted and the other is ignored. And the other graph is where the other port is contracted and the first port is ignored. Each tree is enumerated by the sum of the conductances on its edges times the conductances on the edges that are omitted. But the different terms in the numerator have different signs. And the signs are determined by the relative orientation of the ports within any cycles that are among the ports when the tree is contracted. So in particular, if the forest is two trees in the original graph, when it's contracted, you get this graph. The choice of positive sign for this kind of forest is intuitive because the battery is pushing electrons into this side to this connected piece of the tree, and that raises the potential of this piece relative to this piece. Okay, now.
I didn't see what the difference was before.
The difference is the two edges are, the two ports are yeah, okay. Okay, now, application of some of what I've been saying, okay, here we go. Raleigh's inequality says that the equivalent resistance across one edge, it might be a port there or might not. No, there might be a resistor on the edge or not, but the resistance, the conductance across one edge increases if you increase the conductance of that edge or any other edge, or the equivalent conductance either increases or remains the same. That's Raleigh's inequality. If you make anything in the network more conductive, then the equivalent conductance is greater or less resistance. Okay? This is equivalent to this inequality obtained by taking derivatives. What I did was use Maxwell's rule to express the conductance across edge E. Now, in fact, this inequality follows from this fact that the right-hand side is the square of something. Okay? Now, this is a notation, a funny notation for the common spanning trees in two graphs, one obtained by contracting edge E and the other by contracting edge F. But I separated the plus ones and the minus ones. Okay, now, Youngbin Cho in 2004 proved essentially the same thing as this identity using arguments based on vertices, the all-minors matrix tree theorem for picking 1, 2, I think maybe 3 vertices, and combinatorial cases, and Jacobi's theorem that relates the minor of a matrix to the minor of its, relates minors of a matrix to minors of the inverse. Now here's a very short proof of the same identity. Let R be the transfer resistance that I had presented before. One case of the results that I'm going to present is that when you formulate the solution to the network in this form, then the determinant of this 2 by 2 minor, in other words, this P by P minor of the behavior description is equal to the ratio of 2 tree sums with positive sign. The numerator tree sum enumerates the trees that you could think either, well, the trees that are in this graph obtained by contracting E and contracting F also. Okay, now, so this is known by electrical engineers. The sign is positive because the R matrix is at least positive semi-definite. But my methods will give a combinatorial proof that's equal to this ratio with that sign. And so you just plug this into to Maxwell's rule applied to other elements of the matrix, and divide through plug these expressions for R into what everybody knows is the determinant of a 2 by 2 matrix. Clear the denominators, and the result follows immediately. So that's the application of knowing this is a plus sign to deriving that the right sign here is a minus there, and you get the right thing. Okay. Now, the same method, of course, generates identities if you apply it to the transfer resistance matrix in 3 ports, or to any other port characteristic matrix that electrical engineers know. For example, the transmission matrix. In the transmission matrix, you think of a system where you constrain the voltage and the current at the same place. And you do that by using feedback to make it, to force it to happen. The same expressions for those matrices come out. Okay, so the result will be that for all graphs with distinguished edge subset P, so the collection of edges I don't have notation for the edges. The collection of, no, I do, I'm sorry. For all graphs where where some of the edges are labeled by labels in P, and the other edges are arbitrary, and the connectivity is arbitrary. So over that domain, we have a function that takes a graph and maps it into an extensor, in other words, one of these tensors, and this mapping gives you this mapping, M sub E of G, is an extensor valued function that obeys the two Tutte identities that I introduced with. Of course, the multiplicative identity can't be true because the multiplication of Grassmann variables is anti-commutative. So the hard part is finding the right sign corrections so that you can write down these identities correctly in exterior algebra, also known as Grassmann-Bayesian variable algebra. So the plan is to deploy exterior algebra and explain how this exterior algebra realizes linear and also graphic-oriented matroids, stuff in matroid theory, minors of matroids and dualization. Then we use Kirchhoff's and Ohm's law to define the object of interest, this extensor valued function, and then analyze the function in terms of linear algebra and matroid theory and oriented matroid theory in terms of extensors. Now, the reason we're bringing matroid theory and oriented matroid theory into the game is that the properties that characterize the terms in the expansion, the description of the set of objects that are enumerated, the description is best given in terms of matroid theory. For example, saying that something is a tree, or saying that a set of edges is a forest in a graph, in matroid theoretic language says it's an independent set. To say it's a maximal forest is in matroid theory saying it's a basis. And a basis in matroid theory corresponds, when you have a representable matroid, to a basis in linear algebra. So that's why we're going to do matroid theory. Okay, so exterior algebra, I won't say much about that. Other people did better. Extensor is a shorthand for a decomposable element, which is simply the product of linear combinations of linear terms in the Grassmann variable. So if you could express this polynomial as a product, if you could factor it, it's called decomposable, and we call it an extensor. The key fact, which I want, if you're not going to take home anything else, please take home this, that the k-dimensional linear subspaces of the underlying space correspond one-to-one with classes of extensors where two extensors are equivalent under non-zero multiplication. Okay, that's the very interesting thing here. Okay, so I'm going to give you details to remember. If we take a full row rank matrix N, it determines, and the columns of N will be labeled by the same labels used for the basis. In other words, we're distinguishing a basis of the underlying space. We're never going to change this basis. Distinguish the basis, then the row space of the matrix correspond to the extensors, and the way you get the way you get an extensor that represents the equivalence class of representatives is by multiplying the rows of the matrix using exterior multiplication. So the idea is you use the elements of the matrix as coefficients for your Grassmann variables, and then multiply, so express each row as the sum of Grassmann variables, and then take the product of the rows. Okay, and if you multiply it out, you'll get that the coefficients of monomials will be determinants of submatrices of this thing. Okay. Now we could standard textbooks give all the facts, but the one key fact is that you can tell if a row vector, in other words, another linear combination of the S's, is in the row space if and only if when you multiply it by extensor n, you get 0. Okay, if you multiply it by n, well, if this is a linear combination of other factors, then you can write it as a linear combination of the other factors, and then multiply it out, and you get a sum of zeros because of the anti-commutativity. And then so if it's in the space, then this is equal to 0. And if this equals 0, then you could expand out by minors and get the coefficients to demonstrate it. You read it in books. Okay, now now in terms of relating linear algebra to matroid theory, parenthesis, I'm going to parenthesize oriented when in the case of oriented. Okay, so what I'm going to say about matroids without parentheses is true for all, and then statements will be qualified for oriented matroids when you add the parenthesized comments. Yes?
Can you help me out by telling me what a matroid is?
Aha. Okay. What's a matroid? Well, okay. Let me see if I have something that will help.
Just gets worse as you go on.
Yeah, okay. Yeah. What's a matroid? Just gets worse. Okay, let's see. What can I say?
I think it's a generalization of a graph.
Yeah, it's a generalization of a graph, a generalization of lots of things.
Is it actually the generalization of the adjacency matrix of a graph?
No, not well. Let me say. I don't know. I tried to. Let's see if I had some motivation. Okay, I'll say what they are. Okay, here we go. A matroid and an oriented matroid is a discrete structure. That is, it's a structure on a finite set. So it's like I'm not familiar. The talk, the material and species. It's a gadget like that. Okay, the n would be the number of elements in the so-called ground set. And I'm not saying what that structure is because there are many different equivalent structures that express the same information. Now, this information expresses, among other things, what are the dependencies among the columns of a matrix? If you have a matrix with labeled columns, sometimes a set of columns will be linearly independent and sometimes they won't. If you abstract that structure, declare what column sets are independent, that gives you the matroid represented by the matrix. So we abstract that kind of discrete structure. Another way, what are the dependencies among the columns? Well, if the field is ordered, each dependency has a coefficient for each column. Each coefficient is either positive, negative, or 0. So you can write out no more than 3 raised to the size of s power formal vectors of zeros, pluses, and minuses. It's just a finite structure. When the zero pluses and minuses come from the signs of the dependencies of the column of a matrix over an ordered field, you get an oriented matroid. So this is abstracted. We write down some axioms that are satisfied by these examples of matroids and say, hey, a matroid is any structure that obeys the axioms. Okay? Now, anyone want to hear the simplest axiom is the independent set axiom. And I'll tell you what that is. A collection of sets. No, I didn't define. I did not present the axioms of matroid theory. So okay, I will. Okay, so a matroid. One way of presenting a matroid is a finite ground set together with the collection of independent sets. And this gadget, this structure is in the matroid species, I guess. I don't know if that's the right way to say it, if it has the following properties. Let's see. The empty set is an element of the independent set. Independent sets. And here we go. If A and B are both independent, okay, and B happens to be bigger than A, then there's an element you can take from the big set, which is not in the small set. And when you stick it into the small set, you get another independent set. So writing it out, there exists an X in the big set that's not in the little set, such that the little set with X added is also independent. Okay?
You forgot the trivial axiom that every subset of an independent set.
Oh, exactly. I'm sorry. Yeah. So these, I think that's not so trivial. Yeah, and then it's closed under subset.
It really helps to make this concrete, to think about what he said earlier about matroid of a graph, where the S are the edges of the graph, the independent sets are the forests,
Yeah.
and your basis, your maximum independent sets, are the trees. And this satisfies this. If you have some forest that's smaller than some other forest,
Yes.
the big forest, there's always some edge in there you can throw into the little forest without creating a cycle. So it just helps make it concrete so you can think through this.
And the second major example is a finite bunch of vectors in a vector
Exactly.
space. Independence means linearly independence, and it's very easy to check that augmentation axiom.
Okay. Well, thank you so much. That really helps. And I'm going to show the matrix presentation of the graphic matroid. So the same matroid that Professor Ellis Monahan told you about, the same matroid can be presented as the matroid of dependencies among columns of a matrix. The matrix is simply let's see. The matrix is simply the signed incidence matrix between vertices and edges, with a funny convention that in each column, one of the ones representing an incidence must be minus, and the other must be 1. So if you find that, any two columns of this matrix are linearly independent, but the set of all three together are dependent. So the independent sets of this matroid are all subsets of E, F, and G, except for everything, except for all three. E, F, and G constitute a circuit. That's a quick intro to matroid theory. Now, in oriented matroid theory, we could.
You have 7 minutes left.
Okay, enough of that. Okay, so the idea is these concepts like the basis, the matroid, the bases of the maximal independent sets, the independent sets for which you can't add another element and get a bigger independent set. Well, if you write out the antisymmetric tensor, the extensor, the Grassmann-Berezhian polynomial, multiply it out as a sum of monomials, the monomials that appear will correspond to the bases of the matroid.
Remind us again, which extensor is this? It's represented.
This is the product of the, basically this is derived from the product of the rows of a full rank representation. So the full rank representation, you see there's a column, there's a row dependency in this example. So it could throw away the bottom row and get the same dependence structure. So you take E plus G wedge F minus G and multiply that out, and you get the extensor that represents this graphic matroid. Now, oriented, the signs of the coefficients, if you're over an ordered field, give you the combinatorial data that defines the oriented matroid. Now, an axiom for oriented matroid, axiom system for oriented matroids can be read out from as the combinatorial condition implied by the Grassmann-Plucher identity. The Grassmann-Plucher identity characterizes those antisymmetric tensors that are decomposable, in other words, which correspond to subspaces. And so, yeah, the idea is that if two sequences are bases, then the product of their pluses or minus things is non-zero, and so it must be that there's another pair of bases that exist obtained by exchange, a suitable exchange, and the signs must be compatible with this identity being true. Okay, so now in matroids we have deletion, contraction, and dualization. Those are really cool. Deletion is easy. In contraction is a little bit harder. In matrix terms, we row reduce to eliminate a column. Okay, reduce the column to a column containing a single non-zero entry, and then remove the row with the one. Basic applied mathematics operation. Now, contraction in graphs corresponds to what everyone knows. You shrink the edge and throw it out. Now, this reduces the rank, except when E is a self-loop in the graph or a zero column in the matrix. In matroid theory, the contraction by a loop is defined, but for us, since we want to mimic the triplet of matroid operations, deletion, contraction, and dual. We want to mimic those operations in exterior algebra so that we can write down identities in exterior algebra that correspond to matroid properties. That's what we want to do. So we want to define the operations on extensors in a way that, number one, mimics the matroid properties, and number two, is well defined in algebra so that we can write down algebraic identities. That's a, sort of a short. So when we contract an element that would not do the typical thing, the result is the zero extensor, okay, which is the additive identity in the algebra. Note well that a zero rank matroid with only the independent set of the empty set corresponds to the multiplicative identity, or a scalar, non-zero scalar in the exterior algebra. Okay. Now, in duality, you get the dual of the matroid. You get the dual of a linear matroid by using a matrix that is the orthogonal complement, whose row space is the orthogonal complement to the row space of the original. That gives you the dual. I'm not going to say much. You could specify the dual abstractly in terms of the complements of the bases of the primal. Go through the primal matroid, list all the bases, and then complement each basis in S. You get a collection of sets of equal size. Bang! That collection of sets will satisfy the basis axioms. It's called the dual matroid. Assign it to your class for homework. Okay, now, the dual of oriented matroids can be specified by this formula on the basis orientation. The sign of a complementary sequence of columns is given by the sign of an arbitrary complement corrected by a parity factor that's chosen in such a way as to make the product invariant of which order you pick for the complementary sequence. So this formula is known as from the Hodge-Star operation in multilinear algebra. But we want it to be well defined. So in order to make it become well defined, we borrowed an idea from calculus on manifolds called pseudoform.
26 seconds.
Okay, you do the right thing, right sign corrections, and then we define the dual property, and here is the construction of the object. It's obtained by writing down the matroids corresponding to the electrical network equations, and then contracting by the edges corresponding to the voltages and currents within the network to leave Grassmann variables labeling the voltages and the currents outside the network. That gives it to you. And here's the result. The sign corrections are determined from the orientation of sets that's chosen arbitrarily. It's chosen so that you could pick any sign for any sequence of elements as long as, when you permute a sequence, you change the sign by the right parity. Otherwise, then using any sign correction together with the same orientation for defining M sub E, then you get the identities where there's exterior product in the multiplicative identity, and there's exterior sum in the additive identity. Okay, so I think that's about it. And this is a matrix tree theorem. This is our generalization of the matrix tree theorem. Each minor of the calculated object. Well, the minors are tiny. They're just p by p. But the number of edges in the graph could be huge. So we're looking at minors of a 2p by p matrix for graphs with any number of edges. Each minor enumerates certain trees certain forests within the graph. That's what happens. A big enumeration of small minor. And then of forests that have common matroid properties given by these two sequences of ground set elements, both being bases in the graphic matroid. That's the matrix tree theorem. Okay, and I'll give you there. I have a couple of. I just gave. I used to use extensor product, and I threw it in the notation of Grassmann-Bayesian integration. I did not bother figuring out how to do the signs correctly. But you can do it, if you know that, you can do it. I made a variation. I expressed Ohm's law explicitly and then stuck that into the product and then divided out by two variables for each edge. Okay. And then here's the example. We start out with the matroid representing this graph.
Minus 93 seconds.
Okay, here's the result before contracting the edges. Here is the result after doing row operations so that we can contract the edges. And then after we remove the columns, we get this object. This is the object we construct, the coefficients of the 3-order minors. And the minors enumerate certain FARs. That's it.
Okay, we have time for about -2 questions. Are there any?
How does one ask that?
Okay, that's one. We now have time for -3 questions. Yes.
I'm interested. I heard this. You were interested in the computing the resistance in electric network.
Yeah.
I just mentioned that in 2 weeks in the workshop following this one, that's in 2 weeks, I'll be giving a talk about physics solution to the resistor problem. So in case you are not here, I believe when the program comes out, there will be references. There are 2 papers. One is on resistance, the other is on impedance, which would involve the complex elements. I don't know whether you have considered the
Well, the algebra works.
The algebra works.
Yeah, the algebra will work.
So there will be some differences.
Yeah. If you use R's and the R's and G's could be complex. No, the same thing.
Okay, let's go straight
Okay,
on
thank
to the last talk this afternoon, which is Razvan